Hello students, in the previous sessions we completed sums that were related to dot product, kinetic energy, fine. So and some of the sums were also related towards the momentum conservation, fine. So you should be clear with all those sums, okay. So we did around like 22 sums so far. So in the session we will do the next 11 or 12 sums, fine. So these sums will be related towards potential energy, total energy, and then vertical circular motion of a bob and those stuff, okay. So all those straight away formulas we will use it, right? Okay, so these sums will also be easy. Let's jump into the sums. Okay, let's see the first next one, which is like the 23rd sum. Got it? So here you have got a body of mass 3 kg which is under a constant force, okay. So you are having a mass that is like 3 kg and there is a force that is acting on that 3 kg mass, fine, which causes a displacement s in meters in it, okay. So because of that force it is going to experience a displacement of s, fine, which is given by the relation s equals 1 by 3 t square, right? So they have given us the relation straight away. With that relation I'll be able to get the displacement, which means d is something that I'll be able to find it, okay, where t is in seconds, fine. Work done by the force in 2 seconds is, okay. So here I'll have to find the work done in the interval of 2 seconds, first 2 seconds, got it? So this is simple, straight away easy sum. What will be the formula for the work done? So that will be like work done which is equal to force times the displacement, okay. Here vector doesn't come into picture because they've given everything in one dimension itself, right? Therefore I do not want to use the dot product, got it? Because both of them are aligned, therefore theta will obviously be 0 degree in the situation, which means cosine theta will be equal to 1. So fd, so here what I have to find is the displacement d. So to get the displacement d, just substitute like t equals 2 seconds in this equation, you'll end up getting the displacement d, okay. For the force, f should be equal to mass times acceleration, right? So they have given us the mass over here, therefore I'll be able to substitute 3 kg for the mass. With the case of acceleration, I'll have to get the acceleration, right? So to get the acceleration, let me use the kinematic equation that I've got, okay. So the kinematic equation that will be needed over here is actually the relation between the displacement and then the time, okay. So that will be the second kinematic equation which I need to use. So it will be like s equals ut plus half at square. So I'll choose that kinematic equation because in this entire question it is pretty obvious we do not know the initial and final velocity, things of that sort, okay. So it will be wise to choose the second option, I mean like second kinematic equation. Got it? So simple sum, just let me do it, we'll get the answer straight away, okay. So to get the displacement d, so displacement d will be equal to s, that should be equal to 1 by 3 t square. So instead of t, let me substitute like 2 square. So you do not want to worry about the initial position because they have given us straight away displacement, okay. So 1 by 3 t square. So instead of t, if I just substitute like 0 initial time, that will be equal to 0, right? So therefore final position minus initial position doesn't come into picture over here because they have given us clearly displacement in and itself is like s. This is not the position, this is the straight away displacement, okay. Got it? It should be clear. Okay. So 1 by 3, 2 square, right? So if I do solve this one, you will have like 4 by 3. That will be the displacement that has covered. So now I'm just done with this d component. Next, what I'll have to do is I'll have to get the acceleration, right? So to get the acceleration, you'll have like s, that will be equal to ut plus half at square. This should be the formula that I need to use, isn't it? So to use this one, you will have like, instead of u, the initial velocity was obviously 0, right? So because of this force, a 2 kg mass is under a constant force which causes a displacement, okay. So only after, okay, so only after the force given to it, that is when the object started moving, okay. So before the impact of force there wasn't any motion, therefore initial velocity has to be 0. By the way, they haven't mentioned anything that is related to initial velocity, therefore obviously that has to go to 0. So the first term will be like 0. So if I do the solving, I'll end up getting the answer. So you'll have like half, a is something that I need to find over here, so a, so instead of t square, let me substitute like 2 seconds, okay. So that will be like 4 over here. For the displacement s, I'll substitute the 4 by 3 that I've got already, okay. Got it? Yes. If I do the solving, I'll get the acceleration a, so those two 4's will get cancelled out. So you will have like a that will be equal to 2 by 3. So now I have got the acceleration a, which will be equal to 2 by 3 meter per second square, right? So now I have found out the acceleration. Next, what I'm supposed to find is actually the work done. So work done will be equal to force times the displacement. Instead of force, let me substitute the mass and the acceleration. So mass will be like 3 kg and the acceleration will be like 2 by 3. Okay. So 3 into 2 by 3 will give you the force. 3 into 2 divided by 3 will give you the force, and then you have got the displacement, that will be like 4 divided by 3. Okay. Yeah, that's it. 1 3 3 will get cancelled out. Yeah, numerator and denominator, those two things will get cancelled out, and then you are just left with the work done that I'm supposed to find, which will be equal to 8 divided by 3 joule. So the answer here is like option 4, which is like 8 by 3 joule. Got it? Right. So this is simple sum. Right, straight away just use the basic formula, just find out the displacement, find out the acceleration, just plug it into the formula of work done, force times displacement, you will end up getting the work. Okay, right, you shouldn't have any doubt on this question. Let's move on to the next one. Next sum is also simple, easy one. Okay, so graphical based sum. Let's see what the sum is. You have got a force capital F acting on an object varies with distance x as shown here. Okay, so you're having like force F on the y-axis, and the same way you have got like displacement x on the x-axis. Okay, so the force is in Newton and x is in meter. Okay, SI units. The work done by the force in moving the object from x equals 0 to x equals 6 meter, right? So whenever you get a graph, it should be obvious. In majority of the situation, I'll end up getting the area under the graph, right? So even in this situation, work done will be equal to integral of f d, right? So here obviously forces along the y-axis and the displacement dx is along the x-axis. Okay, therefore it is pretty obvious. Just getting the area under the graph will give you the answer. Okay, because I need to find the area work done over here, right? So here just calculate the area under the graph, you will get the final answer. So in the situation it will be like 3 along the x and then 3 along the y, therefore 3 into 3, that will give you like 9 joules. So for the first part you'll have like 9 joules, and same way for the triangle you'll have like 6 minus 3, that will give you like 3, and then 3, that's going to be 9 divided by 2 will be this one. Okay, so over here the area will be like 9 divided by 2. Okay, if we just do the addition of those two stuff, I'll end up getting the answer. So you have got like 9 plus 9 divided by 2, which is like 4.5. So that will give you like 13.5. So the answer here is 13.5 joule, which is like option 2. Okay. So simple stuff, right? You shouldn't have any doubt on this question. Let's move to the next one. Next question is simple conceptual based sum. Let's see what the sum is. You have got a man who is slipping on a frictionless inclined plane and a bag falls down from the same height. Okay, so you got a guy who is standing on an inclined plane. By the way, there isn't any friction between the guy and then the plane. Okay, so that surface is frictionless, and then he got slipped from the topmost point. Okay, so he is just slipping and sliding on this inclined plane. Same way, while he was about to slide, he has dropped a bag which is going to fall vertically downwards. Okay, so that's what's going to happen. Then the velocity of both is related as. Okay, so I have already told you this is a kind of conceptual based sum. So they're asking us to relate between the velocities, right? So they have given us Vm be the velocity of the man and Vb be the velocity of the bag. Okay, so I'll have to get the relation such that which one is greater, Vb greater than Va or something other than that. Okay, I'll have to get that relation. In this situation, I do not want to consider the direction, only the magnitude is considered. Okay, because it is pretty obvious. Only thing that they're asking us over here is actually which one is greater, right? Therefore here I'll just have to get which of the parameter is greater, right? So let me draw the diagram for the question over here. So you have got a guy who is standing on an inclined plane. Okay, there is a guy who is standing on an inclined plane, and what he is doing is he just got slipped, and then he is slipping down on this inclined plane. Okay, and then he reaches the bottommost position. Same way, while he was about to slip, he has dropped a bag from this position. Okay, so he is having a backpack which got fell down from this point, and that too is going to reach the earth's surface, right? So if that was the case, then what will be the velocity with which it is going to reach the earth's surface? Obviously in this situation it only depends on the acceleration due to gravity. Okay, Therefore, in this question, it should be pretty obvious. Both the person and then the backpack is going to reach the Earth's surface with the same velocity, because only acceleration that was acting over here is actually the acceleration due to gravity, right? Which was downwards, right? With the case of the person, he is going to reach the Earth's surface with certain inclination. So the velocity, direction of the velocity will be inclined at some other angle. But with the case of the backpack, it is just vertically falling downwards, right? So whatever the case it is, whatever energy stored, that will be released. Therefore, when they are about to reach the Earth's surface, they will reach with a constant velocity, right? So we have discussed this concept multiple times, right? You should be clear with this idea and notion. Therefore, here in this situation, VB should be equal to VM. Therefore, option 3 will be answer, right? Simple conceptual based sum. You shouldn't have any doubt on the sum. Let's move to the next one. This sum will be like little bit lengthy. I'll just tell you extra more concepts that are needed to solve this sum, okay? So I didn't teach you this concept in the theory part, fine. So you need like extra one understanding to solve this sum, right? I'll just tell you, right, while doing the sum. So here you have got the potential energy of a particle in a force field, which is U, that is equal to some equation, A by R square minus B by R, okay? So they have given us the equation where capital A and capital B are positive constants and R is the distance of the particle from the center of the field, okay? So they have given you potential energy of the particle at different instant in that particular field, okay? So you have gotten force field, whatever it is, whatever force field you have got over there, and then you are just going to place an object at certain distance r from the origin, okay? So at different position of r, to get the potential energy at that particular position, I'll use this equation, okay? So where r is the display, it's a kind of like distance of the particle from the origin, it's a kind of displacement over here, right? So here, to get the potential energy at different points, so I'll have to use this equation. Got it? For stable equilibrium, the distance of the particle is, so in order to achieve stable equilibrium, so at what distance should the particle be placed from the origin? That's what I need to find, okay? So I'll have to get that particular R. So this R is a kind of like radially emanating lines from the origin, okay? Got it? So first I'll have to explain what is meant by stable equilibrium, right? So to get the stable equilibrium, how should I actually operate with this equation? That's what I need to get, right? So I'll give you like two conditions that you need to know, right? So this is a kind of small theory that I'm going to teach you, okay? So you have got like two bowls, okay? So you have got like two bowls. One is actually placed properly and the other one is placed flipped, okay? Got it? Same bowl, but in the first case I've just placed it in a normal position. In the second case I've just flipped it and then placed it on the table. Got it? So there are like two balls. Got it? And then I'm just going to place a ball in the first ball at its bottommost position, okay? So when I place it at its bottommost position, it is pretty clear this is stable, right? If I just give a small push to it, initially the potential energy will be like zero, right? Because it is in the bottom position. So when I give like slight push to it, it will start oscillating, right? So when I give a slight push to it, obviously it will just move with certain kinetic energy. Then it will reach its maximum height. Again, it will just move downwards. So there will be an oscillation. Because of that oscillation, it is pretty obvious this position is a kind of stable equilibrium, because it will again come to its mean position. And then when it releases its energy to the surrounding, it will reach the stable point. That is why I call it as like a mean position or the stable equilibrium in this case, okay? So this first condition is actually stable equilibrium. So whenever you give push to that particular object, it will again return back to its mean position, or else it will return back to its old position when the energy has been removed. If that was the case, then it is called a stable equilibrium, right? So it is pretty obvious when you look at the picture, right? So the next one is obviously the unstable equilibrium, right? So here you have got like unstable equilibrium, okay? So the name itself clearly suggests that when you're in the situation, I'll just place the object on its topmost position, okay? So this is a kind of unstable equilibrium, okay? So when I place it at its topmost mean position, so here it is obvious that will be at rest. There wouldn't be any motion into it and it is perfectly balanced. Same way you are having like acceleration due to gravity downwards, right? But if you just give a small push to it, it will just fall down, right? So in that mean position, it was at rest, everything was balanced. But this position is actually an unstable equilibrium. So if you just give a slight push to it, it will just fall down, right? Okay? So that's the understanding that you need to know. So when the object is in stable equilibrium, it will be at that point. When it loses its energy, it will return back to its original state, okay? But with the case of unstable equilibrium, once you give a slight push to it or slight external energy to it, it will just lose its equilibrium and then it will go to some new other equilibrium position, but it will never return back to its original state, okay? So that is what is meant by unstable equilibrium, right? So you have got like two different cases over there. So here in this question, they are asking us to find the stable equilibrium, right? From the understandings that we have developed, it is pretty obvious. If it was like stable equilibrium, it has to be at its bottommost position. So when this object was at the bottommost position, we have got the potential energy to be the minimum or zero, okay, depending on the situation. Same way for the unstable equilibrium, then obviously this object has to be at its topmost position, okay. So here the potential energy has to be maximum, okay. Here, if I give push to this particular object, the potential energy was at minimum or zero. When I gave that push, the potential energy increased, right, to some maximum value, and then it got decreased, fine. So then obviously in this situation, they're asking us to find the stable equilibrium. Therefore, in this condition, this object should reach some minimum potential energy, right? I'll have to get that point where the potential energy is minimum. Rest all other position, it has to be greater than this minimum value, right? So in this bowl, if I'm just going to place this particular particle on any other position, obviously that will be greater than the potential energy at its minimum point, right? So same way, I'll have to get the minimum potential energy point for this particular equation, right? So that's the thing, that's the answer that I need to get from this equation, right? So to get that answer, what I have to do is I'll just have to do the differentiation and I'll have to equate it to zero, right? So this is a kind of concept that we have already learned in the motion in a plane chapter, right? So I have just taught you a kind of extra concept which you need to know, right? So I'll just input that one. So if they've given you and graph and they're asking us to find the minimum and maximum point, what will I do? I'll just do the first differentiation and I'll equate it to zero, okay? So in that, if I do that one, I'll end up getting either the minimum point or the maximum point, right? I've already taught you in the motion in a plane chapter, right? You should be clear with that graphical stuff, okay? So to solve the sum, first I'll have to differentiate this equation, right? And then I'll have to equate it to zero. If I do that one, I'll end up getting the minimum or maximum point, right? In this question, they have just clearly told us that that equilibrium is going to be stable equilibrium. Therefore, it should be the minimum point, right? To verify that whether it is a minimum point or a maximum point, okay, what I'll have to do is I'll have to do the double differentiation to get that answer. If I do the double differentiation, if I get the answer to be like negative, then that is like maximum. If I get the answer to be like positive, then that will be like minimum, right? Okay, so that was the understanding that we have already developed while doing the chapter motion in a plane, okay? So I'll use the same logic and understanding over here. Let me draw the diagram. You'll end up getting a clear more idea of what I'm telling you, okay? So you have got like two different graphs for these two different scenarios, right? In this situation, what I'm going to take over here is actually the position along the x, okay? That will be the displacement, whatever it is, like position along the y or x, but the displacement will be along the x-axis, okay? So you have got like displacement along the x-axis. Same way for different positions along the x, what will be the potential energy? That's what I need to find, okay? So if the x was like 2 meters, then this would have covered some extra y along that particular bowl, and then it will be at its new position where you'll have some potential energy stored into it, right? So based on the position of x, the potential energy will increase proportionally. Got it? So here I'm just going to relate it between the displacement and then the distance or displacement along the x-axis, same way, and then the potential along the y-axis, okay? So you will have like potential along the y-axis, got it? So that's how it has to be related for this particular situation, right? So you are going to have u along the y and then x displacement along the x-axis, right? So now I'll have to draw a graph for this scenario, right? So whatever the equation that you get, it doesn't matter. It could be like quadratic or the power could be like 3, 4, whatever it is. But it is pretty obvious there will be a position where it has to reach its minimum. So that will be at its lowest point in the situation. Then as it keeps on moving along the x, you will end up getting the potential energy, right? So when x was equal to 0 or the mean position, you got the minimum potential and then the potential started increasing, okay? Therefore, you will have something curve that will be like open upwards, okay? So this necessarily need not be quadratic equation. It could be any other equation, okay? It could be power 3 or 4 depending on the situation, right? So here in this case, this is a curve that's going to be like open upwards. Okay, so the potential energy will be minimum when it is at its bottommost position. Okay, so here this will be the graph. Same way for the unstable equilibrium, if I have to draw an equation, then obviously that will be like a curve open downwards, because when it is at its mean position, you will have the maximum potential energy. When it moves away from that mean position, you will have decrement in that potential energy. Okay, so here in this situation, you'll have like a graph that will be like open downwards. Okay, so here I've got a graph that is like open downwards. Okay, so depending on the equation, I'll end up getting this graph. Okay, so it's not necessarily a parabola, right? Whatever equation that you get in, you will have a curve, right? So in the first situation, in the first situation, you have the potential energy to be 0 at its bottom position. Okay, which means minimum. Same way in the second situation, you will have like potential energy to be maximum. That will be the unstable equilibrium. That's the notion that you need to know. To get the minimum or maximum position, the slope has to be 0, right? So to make the slope to 0, first I'll have to differentiate the given equation, and then I'll have to equate it to 0. So once I equate it to 0, I'll find the point where the potential is going to change. So that point will be the position where you will have the slope to be 0, right? Tangent of that particular slope to be 0. So over here, I'll have to get the tangent for this particular equation, that is the differentiation. Then I'll have to equate it to 0 so that I get the point where the potential is about to change from one pattern to the next pattern. So here, this will be the point where the slope will be equal to 0, right? So here I've got the slope to be 0. Same way, this will be the position where slope will be equal to 0, right? So if first one was the case, I'll get the stable equilibrium. Same way, if second one was the case, I'll get the unstable equilibrium, right? So in this question, they have given the relation between the u and then the r, right? So it should be clear. U is something that is plotted along the y-axis. Same way, r is nothing but the x in this equation, okay? So r is the displacement. That is what I've plotted along the x-axis. Therefore, the relation is between u and then the r, okay? So here I just need to get either the minimum or the maximum point, right? In this question, they have given us it is like minimum, it is like the minimum point, therefore it is like stable equilibrium. Let us verify. I'll just do the double differentiation and I'll figure out that term will be like positive, therefore that will be like stable equilibrium, right? Okay, got it. So now just do the differentiation of this one and equate it to 0, you'll end up getting the answer. That's it, finished. Fine. So only the conceptual part is like something that I've taught you, but while doing the sum, this is a kind of easy sum. Just get the equation that they've given in the question, equate it, differentiate it, and then equate it to 0. That's it, you'll get the answer. Okay, so the question, so the equation that they've given in the question is u, which will be equal to a divided by r square minus b divided by r. So you have got like a divided by r square minus b divided by r. So that's the equation that they have given. Let me differentiate it and then I'll equate it to 0. If I do the differentiation of u and then the r, okay, so you have got like u along the y and the r or x along the x-axis. Okay, so if I do differentiate du by dx, I'll end up getting the tangent for this particular graph, right? Then I'll have to equate the tangent to 0 to make that slope to 0. Okay, so once I equate it to 0, I'll find the minimum or maximum point. Okay, that's the logic and intuition which you need to know. Simple sum, right? Let me do the solving. So du by dr, which will be equal to, let me do the differentiation over here. A is a constant, they've given in the equation clearly, right? So a will be like constant, and then you have got like r power minus 2. Okay, so that will be like n x power n minus 1. Okay, so n minus 1 will be like negative 2 minus 1, so that will be like r power minus 3. Therefore, you will have like r cube in the denominator. Same way, that n power will come to the coefficient. Therefore, you'll have like negative 2. So here, over here, you'll have like negative 2. Got it? The next differentiation will be negative of b divided by r. So same way, you'll have like r square in the denominator. Same way, you'll have like r square in the denominator, and then you'll have the b, which is like constant. Okay, so that will be like nx, right? So here n was like r power minus 1, so negative 1 will come to the coefficient. So these two things will get multiplied and it will become positive, right? So I have just straight away put the correct sign itself. Therefore, I do not want to change anything with respect to this equation. So now I have got this du by dr, the differentiation of that particular term, what I'll have to do is I'll have to equate this entire term to 0, right? So the next thing is I'll have to equate this term to 0. So if I do equate that one, I'll get the R that is needed. Fine. So let me rearrange this one. So you'll have like 2a divided by r cube, which will be equal to b divided by r square. Okay. So here r square and then the r square will get cancelled out. I'll have to get the r, right? So r will be equal to 2a divided by b. Okay. So the answer should be like 2a divided by b, which is like option 2. Fine. So now I have got the answer, which is like 2a divided by b. I do not want to do the double differentiation because they have clearly told us this is a kind of stable equilibrium situation, which means, yeah, this will be the position where that particle will have the lowest potential. Okay. So if it was like stable equilibrium, then the double differentiation of that particular term has to be like positive, right? So only if it is positive, that will be the lowest point, right? So for the minimum, the answer should be like positive. For the maximum position, the answer should be like negative, right? So here the minimum will give you the stable equilibrium. Therefore, let me do the double differentiation. You will get the answer to be positive. Okay. So if I do the double differentiation for this particular stuff, you will have d square u divided by dr square, which will be equal to the differentiation of this entire term. Yeah. So that will be something like this. R cube will give you, so minus, no, that will be like positive, therefore it will be like 6a divided by r power 4. Okay, I have done the differentiation straight away, so that one should be like clear. Then you have got like negative of 2b divided by r cube, right? So negative of 2b divided by r cube. Yeah. So here what I'll have to do is, now I just got a term, one is positive and the other one is negative. Okay, now I'll have to verify that this entire term is going to be positive. Okay, so to get this entire term to be positive, what will I do is I'll just substitute this r into this equation, because I need to get that, I need to get for that particular position what will be the double differentiation. Okay, so that double differentiated answer has to be positive. If it was like, quadratic equation, then in that situation it will be easy because you will not have any r into it, but in the situation you still have variable into it. So I'll have to substitute this term that I've got over here into this equation, so that I'll find the answer to be positive, because you have got, if I've got like two different equation over there, right? One is like positive and the other one is negative, but I know this is like a stable equilibrium, which means at its minimum position, therefore the answer will be positive. If I do substitute this r into this equation, I'll get the answer positive, right? So let me do one more step to it, you'll end up getting the answer. Okay, so if I kind of substitute 6a, yeah, you have got like r power 4 into it, right? Yes. So let me factor out one more step so that let me do it easily. So if I just factor out like 1 by r cube from this equation, you will just have 6a divided by r minus 2b, right? So the only parameter that I need to solve over here is actually this term inside it. If this entire term inside is positive, then obviously r cube is going to be positive because this term is positive. Therefore, 1 by r cube will be like positive, right? If only this term is going to be positive, that's it, finished. I've got the answer, which is called a stable equilibrium, right? Let me substitute like 2a by b over there. So you will have 1 divided by r cube, which will be like 6a divided by, yeah, what do you have over here? You have got like 6a divided by 2a by b, right? So that b will go to the numerator, minus 2b. Okay, so if I do the solving, you'll have a will get cancelled out, so you have got like 6b minus 2b. Yeah, so 2 will also get cancelled out, so you have got like 3b minus 2b, that will give you like b. So here you have got b divided by r cube. So it is pretty clear this term is actually positive. If this term is positive, then the point that I found is the minimum point, then obviously that is a stable equilibrium, right? So here in this condition, they have given us clearly this is a stable equilibrium position. Okay, so it should be a minimum point. I just verified it by doing the double differentiation of du by dr, right? By doing one more differentiation of the du by dr, right? So this sum you should be clear. So in this sum, the concept is something that I've taught you. That's why this sum seems to be lengthy, but actually this sum is easy, right? If you just get such a kind of question, what you'll have to do is you just have to take that equation, just do the differentiation and equate it to 0. You will end up getting the minimum or maximum point, right? If they have given us clearly that that is like stable equilibrium, then obviously it should be a minimum point. If they have given you like unstable equilibrium, then that should be a maximum point. Okay, so that's the idea and notion that you need to know, right? So once you have got that answer, that will be my final answer, right? In order to verify that one, okay, so that is something that you will not be able to do it in the examination. That's not needed also. Just do the differentiation, equate it to 0, you'll end up getting the answer. Just to verify it, I just put one more extra step into it, which is like double differentiation of it. That one has to be positive for that particular term. That is when I have reached the correct answer, stable equilibrium. I did it and I got it to be like positive, therefore that is a stable equilibrium position, right? Fine, you shouldn't have any doubt on this question. It should be clear, simple one. Let's move to the next one. This one is simple statement based sum. Let's see what the sum is. You have got the potential energy of a system increases if work is done. Okay, so in what fashion work has to be done so that potential energy is getting stored into that system. Okay, upon the system by a non-conservative force. So you're having a non-conservative force, so something is pushing that particular system or object. Okay, so in that situation, obviously that system will end up getting the kinetic energy, therefore in that case potential energy is decreasing, right? Okay, so here I'm just going to give a force on that particular object. Because of that force it is going to move. By the way, this is a non-conservative force, so when you have like non-conservative force, obviously I'll not be able to get the energy back. Okay, so first one isn't true, that is pretty obvious. Then the second option is like by the system against a conservative force. Okay, so non-conservative force is a kind of frictional force, is a non-conservative force. Okay, and then some other nature of forces in the surrounding will be like a non-conservative force. So the wind that is acting, everything will be like a non-conservative force. But here for the second option, it is pretty clear. It is moving against, I mean the system is moving against the conservative force, which means in this situation I'm just going to throw a ball from the earth surface. So when the ball is about to move, I just gave the entire energy, therefore the ball is having certain velocity into it, therefore that system is moving against the acceleration due to gravity. So that will be the case when the energy will get stored into it, right? Therefore option 2 will be the answer for this question, because that will be the case where the system potential energy will increase, right? So if you look at the rest two other option, you'll have like by the system against the non-conservative force. So when it is moving against non-conservative force, friction or air drag force, in that situation, obviously I'll not be able to get back that energy, because that will get released to the surrounding in other forms, right? So that is a kind of non-conservative force. Obviously option 3 will not be my answer. Same way, upon the system by a conservative force. So when I give force and then because of that force the object is going to move, in that situation I'll end up getting the kinetic energy, therefore energy will not be stored. All the energy that got stored is getting released, therefore potential energy will decrease, right? It is obvious. Option 4 shouldn't also be my answer, right? You have to be clear with this question. Let's move to the next one. This question is based on the concept of vertical circular motion of a bob that you have learned in the theory. Got it? So from this question onwards, you'll get around like 7-8 questions that are related to that concept, right? So you should be clear with that concepts that we have learned. So here you have got a mass of M, which is attached to a thin wire and whirled in vertical circle, right? So this is vertical circular motion of this particle mass. Okay, the wire is most likely to break when. So at what instant the wire will break? That's what I need to find. So here, this is a kind of logical based question. So let me draw the diagram for that vertical circular motion. So you have got a string which is hinged at one position, and on the other end you have got a mass or bob. Okay, so this entire setup is going to whirl in a vertical circular motion. So this is going to move in a vertical circular motion. Okay, right? So this is going to move in a vertical circular motion, right? So if the velocity that I gave at its bottommost position was equal to root 5 gr, so that will be the optimal velocity. So if the velocity was equal to this one, then obviously this will be able to make the vertical circular motion. If the velocity was less than this root 5 gr, then it will not make that complete revolution, it will just fall in between. So it will just move up to certain distance and then it will fall in between itself. If the velocity was equal to root 5 gr, then when it reaches the topmost position, that will be the point where the tension will be equal to 0, which means the string will get slackened at its highest point. Okay, so this was the optimal velocity. Therefore, when it has reached its maximum position, the acceleration due to gravity or the gravitational force in itself is good enough to make that circular turn. Okay, so that acceleration is good enough to give that necessary centripetal acceleration for that particular vertical circular motion, right? So that's the idea and concept that I've taught you in the theory part, right? You should be clear with that concept. So here what they're asking is to find is actually what will be the position when the string will break. Okay, so initially when the bob was hanging, it was actually balancing this mg, that will be the tension over here, right? So when I gave a force or horizontal velocity in the situation, you actually need extra centripetal force inward. So you will have like tension because of the mg, and also you will have mv square by or extra centripetal force that is required for this bob to move in a circular motion. Okay, as it starts moving upwards, obviously the velocity will keep on decreasing, therefore proportionally tension in the string will also decrease, and then it will come to a point where the tension will go to 0 or minimum. That will be the highest point, right? So that's the idea that I've taught you, right? So from this understanding itself, it is pretty clear when the bob is at its lowest position, you'll have the maximum tension acting on the string. Okay, so at the lowest position, you'll have the maximum tension. At the highest position, you'll have the minimum tension, right? If the velocity was optimal, then at the highest position, the string will get slackened and the tension will be 0, right? So obviously, it is pretty clear. At its lowest point, you got the maximum tension acting in the string. Therefore, that will be the point where it is most likely to break, right? So I'll have to get that point from the option they have given in the question. So first one they have given inclined at an angle of 60 degree from vertical. Okay, so that's certain 60 degree. Obviously at this position tension will be less when compared to the lowest position. The mass is at its highest position. When it has reached the highest point, tension will be minimum, or in the perfect situation it will be equal to 0. The wire is horizontal, that too doesn't make sense. You will still have tension into it, minimal tension into it. The mass when it is at the lowest point. Okay, so when it is at the lowest point, it will balance everything. It will balance the perfect mg, and then it also have to produce the required centripetal force for that particular bob to move in circular motion, right? So after that, the tension will keep on decreasing because the velocity will also decrease. Proportionally, the impact of the mg will also decrease. Okay, fine. So from the concept that we have learned, I've made an argument which should be clear to you. So the answer over here is option 4, right? So this is a kind of conceptual based sum, right? So just look into the question. If you are clear with the idea and the concept that I've taught you, you'll be able to get the answer straight away, right? So you should be clear with this question. You shouldn't have any doubt on this question. Let's move on to the next one. This question is also a simple one based on the concept of vertical circular motion of a bob. So here you have got a body initially at rest and sliding down a frictionless track from height h. Okay, so this surface is frictionless as shown in the figure. Just to complete the vertical circle of diameter AB, which is equal to d. So it has to just complete this circular motion in this loop. The height h should be equal to, right? So here I have to find this height h, right? So that this body which is moving along this inclined plane is good enough to make this vertical circular loop. Okay, by the way, they have given us this diameter AB equal to d. Okay, so they have given us the diameter over here also. So in this situation, if I do the solving, the velocity that is needed at this point A should be equal to root 5 gr. Only if this velocity is equal to root 5 gr, it will be able to make this complete turn. Okay, right? So if the velocity was equal to root 5 gr, I've got the, I'll be able to get the kinetic energy which will be equal to half mv square, right? So that much amount of kinetic energy is needed at this point when it reaches the point A, the bottom point. Okay, so if the kinetic energy has to be equal to half mv square, then at what height should I actually have dropped this one to slide? So that will be equal to the potential energy, right? So that should give me the potential energy which will be like mgh So the mgh should be good enough to produce that much amount of kinetic energy. If I have that optimal kinetic energy, I'll be able to make the vertical loop. Okay, just do the energy balance, you'll get the answer. That's it, finish. Straight away answer. So the required potential energy should be equal to mgh. That potential energy has to produce a kinetic energy which will be equal to half m v square. V square will be v should be equal to root 5 g r. Therefore v square will be equal to 5 g times capital R. Okay, so I'll replace this capital R by d by 2. Okay, because in the question, in the option, they have given us the diameter. Therefore here I'll just replace it with d divided by 2. If I just do the solving, I'll get the answer. Simple question. So H is something that I need to find. M, G will get cancelled out. M, G will get cancelled out. Just do the rearrangement with respect to H. I'll get the answer. Yeah. I even don't want to do the rearrangement. H will be equal to 5D by 4. Okay. So the answer here is option 4. Simple sum. Straightforward simple sum, right? You shouldn't have doubt in this question. Let's move on to the next one. In this question, they're just asking us the formula straight away, right? Simple one. Let's see. What is the minimum velocity with which a body of mass m must enter a vertical loop of radius capital R? Okay, same intuition, same logic that we have seen in the previous question. Okay, what should be the velocity with which it has to enter the bottom point? Okay, must enter a vertical loop of radius capital R so that it can complete the loop. So what they're asking us over here is what is the minimum velocity with which it has to enter, right? So that should be equal to root 5 gr, same as that of the previous question. Here just they have asked us to find only the formula that has to be memorized, right? So the answer over here is like root 5 gr. You should be clear with this question. Let's move to the next one. This sum is logical based sum. What they have given over here is a particle with total energy E is moving in a potential energy region Ux. Okay, so they have given us the total energy, right? So that's the total energy that the particle has, the particle is possessing. Okay, motion of the particle is restricted to the region when. So how should the energy and then the potential has to be related? That's what I need to get, right? So let me take this simple situation. So once you are clear with that situation, you'll get the answer straight away. Simple situation that I normally choose. So here as usual, and this is the earth surface. I'm going to throw a ball from the earth surface. Okay, and then it will reach the maximum position. Okay, so it can't go beyond this region. Okay, because once it has reached the maximum position, whatever energy that I gave got stored into it in the form of potential energy, right? So it can't go beyond that one because that's the amount of energy that the particle is possessing. Okay, so it can, if it was an idealized situation, it will just fluctuate between this region. Okay, it will just keep on repeating this pattern again, but it will never cross this maximum position because that's the maximum energy it has got. Okay, so if that's the case, then obviously at its topmost position, what was the potential? The potential of Ux was equal to E. Okay, because you will not have any kinetic energy. Same way, X actually means the x-axis over here. Let us consider the vertical direction to be X in the situation. So U at the X at the lowest point will be equal to 0 because you will not have any potential into it. So the potential energy has to fluctuate between the E and then it can fluctuate to 0. It can't go beyond the total energy, right? So that will be the region in which this particle will keep on moving. Okay, so either it could be equal to 0 or it could be equal to E or it could be between 0 and then the E. Okay, so Ux should always be less than E or it could be equal to E. It cannot be greater than E. That is not possible, right? So the answer here is option 3. It can be less than or equal to, right? Simple sum. So you'll have to get an understanding of this concept. From that concept, I'll have to get the equation. That's it, finished. Okay, if Ux is less than E, yeah, that condition is possible, right? If Ux was less than E, that is possible. Same way, equal to E is also possible. Equal to 0 is also possible, right? Greater than E, option 4 is not possible. So the best option over here is in which zone this particle will be restricted. That's what they're asking us to find. When it is equal to 0, that is also possible. When it is equal to E, that too is possible. So I'll have to get the Ux that is less than or equal to E. Okay, so that will be the region where this entire particle will be able to move, right? So this one should be clear. You shouldn't have any doubt on this question. Let's move to the next one. Next question is, you have got a roller coaster which is designed such that the rider experience weightlessness as they go around the top of a hill. Okay, so here they have given you the term weightlessness. Okay, so weightlessness is something that we could feel in the lift, right? So in the laws of motion chapter, I've taught you that lift concept, right? So when the lift is about to move downwards, accelerate downwards, in that situation, the weight that I'm going to see in the weighing scale will be less. Okay, so you should be clear with that idea, right? So the normal reaction will be equal to mg minus ma, because I have taught you exhaustively that fictitious force and all those things, right? So if ma, acceleration with which the lift is about to move downwards, is also equal to that of the mg, acceleration due to gravity, in that situation normal reaction that will act on me will be like 0, right? If that's going to be the case, mg minus ma, that will also be mg, therefore the normal reaction will be 0. Okay, so if that was the case, when something is freely falling from top of a hill or something of that sort, only under the influence of the gravity, okay, you shouldn't like use the parachute, just you're just going to dive from the sky, okay, or from the plane. So in that situation, we will be able to experience the weightlessness because we are just falling only under the influence of acceleration due to gravity, right? So there isn't any other object that is going to push us upward so that we do not feel the normal reaction. Okay, so if that was the case, that condition is called as weightlessness, right? Just jumping off from the flight or the cliff, okay, before you just open the parachute, that condition is called as weightlessness because there will not be any normal reaction acting on our body. Okay, just freely falling is called as normal reaction. Okay, so here how are we actually going to design the roller coaster is, we are going to design the roller coaster such that we experience weightlessness as they go around the top of a hill. Okay, as the radius of curvature of that roller coaster is actually 20 meter, the speed of the car at the top of the hill is equal to, so I need to get the speed of the car at the topmost position of the hill. Okay, so here you have got a roller coaster that is going to move in a vertical circular loop. So when the car is at its topmost position, I'll have to feel the weightlessness, which means there shouldn't be any force acting on me. Only thing is gravitational force is the only force that should act on me. Okay, if I have to design it in such a fashion, what should be the speed of the car at the top of this circular loop? Okay, so it has to be equal to root gr, right? So that's the vertical circular motion of a bob that we have learned, right? So it has to be equal to v root gr. If it was equal to root 5 gr at its bottommost position, when it has reached the topmost position, you will have the velocity to be like root gr. If it was less than this root gr, then obviously it will fall off before making that vertical circular loop, right? If it was equal to this root gr, then there wouldn't be any tension, which means I do not want any centripetal force at the topmost position. Just the g will be good enough to balance. So at this point, I'll feel the weightlessness because only acceleration due to gravity, that was the centripetal acceleration that is acting on me. Therefore, that condition is like weightlessness. If the velocity was greater than this one, then obviously I just want to break this circular loop and I'll have to make a bigger loop. I wish to make a bigger loop. Okay, so you will have like tension that will act downwards, right? So you will have that tension given by this rail track. That also shouldn't be the case. Okay, if you have like tension that is acting downwards, then if you put a weighing scale between me and then the car, I mean, in a flipped fashion, you will still have that normal reaction. So I'll be able to feel the little bit of that squeezing, which is called as weight. Okay, there shouldn't be any squeezing between me and then the rail track. Okay, which means I do not want any other force given by the track to me other than the gravitational force. Okay, so that gravitational force in and itself should be good enough to make that circular turn. Okay, there shouldn't be any tension in the string, there shouldn't be any extra force given by that track. Okay, so that optimal velocity should be equal to root gr. That is when I'll feel the perfect weightlessness. Okay, got it? So v should be equal to root gr. Anyway, we have learned this concept multiple times in the theory part itself, so that should be clear, right? So you will have like root of what is the g over here, they didn't give anything, so I'll take it as like 10, and the radius over here is like 20. Okay, so here it will be like 10 root 2. So instead of root 2, I'll substitute like 1.414, so 10 times 1.41, so that will give you like 14.14, right? So here they are asking us the range. Okay, the speed of the car at the top of the hill is between, exactly it should be equal to 14 meter per second or 14.14, or else I'll have to get the range 16 to 17. So that actually deviates much more further. Okay, then if you just look at 13 to 14, so 14 is the optimal. If I go less than that, obviously then I'll fall back. If it was equal to 14 to 15, that seems to be the perfect sweet spot. Okay, so 15 to 16 is something greater than 14 to 15, therefore 14 to 15 will be the sweet spot with which I'll have to make this vertical loop so that I could feel the weightlessness at the top of that position, right, top of that particular hill. Okay, so the answer over here is option 3, right? I'm just choosing the best option over here because the answer was like 14.14. So that value should actually fluctuate between 14 to 15. So that will be the perfect sweet spot so that I can feel the weightlessness at the top of the hill, okay, at that circular loop, right? You should be clear with this question. Let's move on to the next one. This question is based on the concept of vector that we have learned. You have got a stone is tied to a string of length L and is built in a vertical circle with the other end of the string as the center. Okay, so I've just hinged one end and it is the mass is moving in a vertical circle. At a certain instant of time, the stone is at its lowest position. Okay, fine, and has a speed u. So they have given us the speed u. The magnitude of change in velocity as it reaches the position where the string is horizontal to the gravity. G being the acceleration due to gravity is fine. So let me draw the diagram for the question that they've given. So you have got a mass that is tied to a string, stone that is tied to a string, and the other end is actually fixed. So the velocity at its lowest point is actually equal to u. Okay. Yeah, the length of the string over here is L. Okay. So the length is like L and it reaches the position of horizontal. Okay. So next it comes to the horizontal position. Okay. So at this position, I have to get the velocity, right? So let us consider this to be the final velocity, which is like v. Okay. So these are the data that they've given over here. What they're asking us to find is the change in velocity as it reaches the position where the string is horizontal. So I'll have to find the change in velocity with respect to the initial velocity. So the initial velocity over here is the lowest position velocity, which is like u. Okay, so I'll have to get the change in velocity. So change in velocity del vector v will be equal to final minus the initial. Okay, so that will be like vector v minus vector u. So that will give me the del v. Okay, so here I know the initial velocity was like equal to u. The magnitude of the initial velocity was equal to u. What I need to get is actually the final velocity in terms of the initial velocity, right? So to get the final velocity in terms of initial velocity, I'll have to do the energy balance. I know whatever energy that got lost will be stored in the form of potential energy, right? So initially the entire energy was kinetic. Whatever the direction it is, I know initially the entire energy was in the form of kinetic energy, therefore half mu square. So this energy has to split it into two parts. One will be for the potential and the other one will be the leftover kinetic energy, right? So you will have half mv square plus the potential. So while calculating the potential, I have to consider only the vertical displacement. So you will have like plus mgh. H over here is actually L. Okay. Let me do the cancelling. He'll get the answer. So m will get cancelled out. What I need to get over here is actually the v final velocity in terms of the initial velocity, right? So v will be equal to v square, right? So here v square will be equal to v square by 2 u square divided by 2, right? So that left hand side will be on the right hand side. Same way, if this goes to the left hand side, you will have negative of gl minus gl, right? So the next step will be like v square, that will be equal to u square minus 2gl. Those two will get cancelled out. Therefore, now I have got the magnitude of the velocity, which will be equal to u square minus 2gl and its under root. Okay. Now I'm ready to find the magnitude of change in velocity, right? So to get the magnitude of change in velocity, obviously first I'll have to subtract these two vectors vectorially, right? Which is like vector v minus vector u. And then I'll have to take the modulus to find the magnitude of change in velocity, right? In this situation, it should be obvious these two vectors are actually perpendicular to each other. One is along the y and the other one is along the x. Fine. So if I have to subtract or add these two vectors, what will I use is actually the parallelogram law, right? So in this case, let me do it this way. You will have like vector v addition of negative vector u. Okay. So these two are actually the same thing, right? So here obviously I'll be able to use the parallelogram law, that result, which is like root of a square plus b square plus 2ab cosine theta and the angle between them, right? So that will give me the magnitude. But in this case, if you look at this case, it is pretty obvious. Vector v is upwards. Okay, so negative vector u will be in this direction. The angle between them is actually 90 degree, right? So as the angle between them is 90 degree, cosine 90 degree will be 0. Therefore, that third term root of 2, I mean like plus 2ab cosine theta will go to 0, right? So I'll just be left with first two terms, which is like root of a square plus b square, right? So del v, magnitude of del v will be equal to, therefore magnitude of del v will be equal to root of a square plus b square. That's going to be like v square plus u square. Okay, because in the situation the cosine theta, that component will go to 0, right? So I'm just left with v square plus u square. Fine. Okay, this is a kind of same thing as the case of finding the magnitude of resultant vector. So we just ended up there itself. So if I just substitute the v that I've got over here, I'll find the answer. So here if I do substitute that one, you will have like u square minus 2gl, because I've squared it, and then you have got like u square, right? Now just let me match it with the option over there in the question. So that will be like, if I just factor out 2, I'll end up getting the answer, right? So if I factor out 2, you will have u square that was factored out, and then you will have like plus 2gl inside the bracket. Yeah, no, minus 2gl, right? Negative of 2gl minus 2gl. Okay, so the answer here is option 1, right? You should be clear with this question, right? So to solve the sum, what we used is we just equated the energies. Okay, so initially it was only the kinetic energy, finally it was the combination of kinetic and potential. So when I equated it, I ended up getting the final velocity in terms of magnitude. So here I'll have to get the magnitude of change in velocity. Therefore, final velocity vector minus initial velocity vector will give you the change in velocity vector. From that, I'll be able to get the magnitude, right? So those two vectors were actually perpendicular to each other. Therefore, the solving was something similar to that of the finding of resultant vector. Okay. You should be clear with this question. You shouldn't have any doubt on this question. Let's move to the next one, which will be the final question for this particular session. This question is also simple logic based one. Let's see the question. You have got a child is sitting on a swing. Okay, so you have got a child who is sitting on a swing. Its minimum and maximum heights from the ground are 0.75 meter and 2 meters. Okay, respectively, the maximum speed will be, so from the all the questions that we have learned, I know the maximum speed will be at its lowest position. Okay, so when the swing is at its lowest position, you will have the maximum speed for the particular child. Yes, so that swing will be between the lowest height and the highest height. So the lowest height from the ground is at a distance of 0.75 meter. Obviously the ground, it will not touch the ground, right? The swing will not touch the ground. Fine. Therefore, it is at a height of 0.75 meter from the ground, and the maximum point that it can reach from the ground will be equal to 2 meters. Okay, so this height is actually 2 meters. Fine. So the swing, so this actually swing is swinging between 0.75 meter to 2 meters. Fine. So the height over there should be between 2 to 0.75. So the net height will be like 2 minus 0.75. That will give you like 1.25. Okay, so this is the net height that got produced over there, right? Yes. Now I'm just ready to do the energy balance. So if I do the energy balance, mgh so should be equal to the half mv square, the maximum kinetic energy, right? So the maximum height that it can reach from its lowest position will be like 1.25 meters. So that will be the maximum potential energy which will get stored in that swing or else that particular child. So when it reaches its lowest position, that is like 0.75 meters from the Earth's surface, that entire potential energy will be released in the form of kinetic energy. Therefore, that will be the highest velocity. That will be the maximum velocity, right? So here in this question, m will get cancelled out. Let me just solve it with numbers. I'll get the answer. For g, I'll substitute like 10. H will be equal to 1.25 because that's the net height. I need to substitute it over here, and then you will have like half v square is something that I need to get. Okay, so v square will be equal to 1.25, okay, into 10 and then into 2. If I multiply 1.25 times 2, that will give you like 2.5, right? So you have 2.5 into 10, so that will give you like 25. So straight away, so v square was equal to 25, then obviously v will be equal to 5 meter per second. Okay, the answer over here is 5 meter per second, which is like option 2, right? The answer is like option 2, right? So this is simple sum. Okay, just get the net height and equate it with the potential energy, which will be equal to the kinetic energy at its lowest position, right? So you shouldn't have any doubts in the sums that we have seen. We have seen around like 12 questions in this session. So all those questions were mainly related to the vertical circular motion of a bob and those kind of questions, and then some questions were actually related to potential and then the kinetic energy, right? So with this, the video gets completed. Bye.